Oh. What's your name? Kirsten. Huh? Kirsten. Kirsten? You can use my glasses. Hey, thanks. Here. Yeah. Awesome. Thanks. Yeah, it's
Continue on with glomerular filtration. So I got a picture here and some points. Let me read from my slide. I say that filtrate is a filtration of the blood. It contains all the plasma components except protein. So the larger proteins cannot be filtered. Things are secreted into the filtrate, and if they're not reabsorbed, they are excreted in the urine. So the urine will contain all the nitrogenous waste products your body doesn't need, like creatinine, urea, uric acid, and other unneeded substances. And so let's kind of talk about how things are first filtered through the filtration membrane. And let's take a closer look at what we looked at before to break this picture. And if you kind of do a zoom in on the podocyte, you can kind of see two things here. The glomerular capillaries have fenestrations. You can see how the podocytes, the foot processes kind of interdigitate and form those slits. The glomerular capillaries are highly fenestrated. We talked about fenestrated capillaries before, and I even gave these capillaries as an example. So they can allow a lot of fluid to be filtered out. However, you kind of want to limit the filtration by wrapping these cells around them and putting these filtration slits. What I wrote before the break, you don't have to necessarily rewrite this, is that the foot process of the podocytes, I say they interdigitate. Forming filtration slits. So both things allow for a lot of filtrate to be formed, but you limit it to small molecules. If you do a diagram of this filtration membrane here, cut through it, you get a picture like this. And so this is the filtration membrane, what you're looking at there. Let's just draw what you see there. fenestrations between endothelial cells. So that represents the capillary endothelium. This is actually the glomerulus itself. Okay, so where they say capillary endothelium, I'm going to put glomerulus. I'm not going to number it. The fenestrations have been measured, 70 nanometers. On the other side, you have these foot processes. This is one cell on its side. The podocyte. And then the foot process is one. So what you're looking at there, I remember when I was looking at this, I didn't know what I was looking at. This is all foot processes from one cell. And the space between them is about 14 nanometers. That's the filtration slit. So the space from here to there is 14 nanometers. That's the filtration slit. That's why only small molecules can get past there. And then these two things are fused together with the basement membrane. I'll put BM, basement membrane. It's a connective tissue that fuses those things together. And so our filtration membrane is the glomerulus, the basement membrane, BM. Like all connective tissues, they're rich in proteins. I put a little negative sign because proteins usually carry a negative charge. So imagine a connective tissue layer with a lot of proteins in it, which are negatively charged. And then you have the foot processes, which comprise the basement membrane. Like I said, filtration slits are a slit that's about 14 nanometers. So based on all this anatomy or histology, whatever you want to call it, the filtration membrane, it filters based on two things, size and charge. Filters based on number one, size. Well, because you got all the fenestrations, a lot of things can get through, but those slits really limited to small molecules. So if it's a difference between a big molecule and a small molecule, it's really, small molecules are favorably filtered through. Also charge. Well, negative usually repels negative because the basement membrane is filled with negatively charged proteins. However, there's so, it would favor positively charged molecules. Favors positive, so I'm just put a plus sign. But that doesn't mean negatively charged things cannot get through. They can. We'll see that. But if there's if there's a preference, it will be for small molecules that are positively charged. All right. So here's another slide I included. I kind of label it 1, 2, 3. 1 is the process. 2, 3, yeah. The direction of filtration, the arrows on the right are showing you. You're going through, the plasma is being filtered through one direction, out of the capillaries into the Bowman's capsule. So here's the real picture of it. From the inside of the capillary, you can see the peppered fenestrations. On the outside, you can see, because the podocyte cell is there, you can see the filtration slits. All right? So the real picture is way more impressive than the illustration. All right, now, so the glomerular filtration, what makes it a good filter? Well, qualitatively, the kidney's glomerular capillaries, they're going to filter blood plasma just like any other capillary bed. However, quantitatively, they're going to do much more. They'll produce about 180 liters of filtrate daily, as opposed to 2 to 4 liters daily from any other capillary bed. So that's a lot of plasma that's filtered. I mean, if you think about it, what's the average blood volume for an adult? About 5 liters. Now, how much of that is plasma? Maybe 2 to 3? So, let's say it's 3. It's 3 into 180. 60? So it's like, yeah, you're like filtering it through 60 to 70 times a day. It's quite a bit. And that's great. If you have toxins in your blood and you want to filter it out, the kidneys will do it. They're filtering your blood 60 to 70 times a day. Now let's kind of look at why you have such high throughput. Let's look at the pressures measured in these capillaries. This is called calculating net filtration pressure, or NFP. NFP, net filtration pressure. It's a simple calculation. What's the force that pushes all of the plasma through this filter? And they put HPGC. Let's just write that so that you can kind of deduce what it stands for. Well, the HP is always hydrostatic pressure. The GC is glomerular capillaries. Okay, so that's just the blood pressure. Good old blood pressure. Now, blood pressure is 120 over 80. What's mean arterial pressure? About 93. Now let's remember 93 is mean arterial pressure, but it kind of drops. Other capillary beds, when we studied it, you can go back and look it up, pressure was about 35. Here it's 55, it's much higher. Okay, so blood pressure, when you get down to the capillary level, is much higher. Glomerular capillary, so that's a regular blood pressure. Now these other pressures we talked about, well, this one we talked about, OPGC, osmotic pressure, right? The O is either osmotic or oncotic. I've seen both of those. But it's the one where, like, you have stuff in the blood and it retains fluids. So that's why the force is kind of in the opposite direction. It's about 30. The third pressure we only consider at glomerular capillaries because Other capillaries aren't surrounded by a capsule. But when you're surrounded by a capsule that's fluid-filled, that's an opposing pressure, because you have to squeeze blood out into a small capsule that's filled with fluid. So they call that HP CS. The CS is like capsular pressure. But anyways, it's 15. The goal is to have enough pressure. Well, the goal is that the hydrostatic pressure, this first one, needs to exceed these other two. So how you calculate it is that's it. You just add up the pressures that oppose your hydrostatic pressure and just hope that it's a positive number. So it's basically about plus 10. So to talk about the concept behind the numbers, okay, the first thing, why is this number so high? Other capillary beds, it's about 32, 35. Why is it 55? So I want you to think about the arterial capillary arterial arrangement. So let's compare this capillary bed to a regular capillary bed that I kind of talked about in another chapter, where it goes artery, capillary, vein, back to the heart. It's not the case in the kidney. In the kidney, it's like artery, capillary, another artery, and into another capillary bed. So it's kind of like a portal system. So for glomerular capillaries, well, actually, let's mention what we talked about before. Regular capillaries, systemic capillaries. Where you had an artery followed by a capillary bed, followed by a venule or small vein that collects all that blood, the gas exchange. That's regular blood flow. However, there's no vein on the other end of a glomerular capillary. You have another arterial. Okay, just like arterial coming in. There's no gas exchange, but throw the whole thing red. Blood coming in, blood going out. So you have arterial, capillary, arterial arrangement. This arrangement is different than the usual artery, capillary, vein. Arterial, cap, vein. The vein provides less resistance, less capital R. In this arrangement, this efferent arterial provides more. So imagine if you have more resistance there, you're going to have more filtration here. It's just harder for, well, I mean, it makes sense to me. That's why. Okay, so that's kind of why we have more filtration, there's more resistance, there's higher pressures, because there's more resistance on the way out, so we have higher pressures, higher higher filtration. And so that's the idea why you have more filtration. There's about 100 times greater surface area too. You got 1 million of these per kidney. That's a lot of surface area for filtration. It's about 180 liters a day. That's about 7.5 liters an hour. That's about, 70 times plasma volume, just filtering that all the time. So there's a term for that. We call that high renal clearance. If you filter 180 liters a day versus 2 liters a day anywhere else. Filter 70 times daily. High renal clearance. If there's a toxin in your blood, it's likely the kidneys will just filter it, get it out of your body. Okay. You keep the nitrogenous waste products in your blood low, as long as the kidneys keep their function up. So here's the lots of surface areas to picture to kind of like show you there's 1 million glomeruli constantly filtering. And so we have a daily rate. Let's kind of study the filtration rate by the minute. The kidneys is receiving about 775 mils of plasma per minute. 125 of that, that's a number to write down. The GFR is normally about 125 mils per minute. Per minute. That's how much you're filtering at the glomerulus. So if it's receiving 775 and filtering 125, that means the other 650 is going out the efferent arteriole to those other capillary beds. Those are kind of the numbers. And of all of those going in, the 775 filter 125, of that 125 that's actually filtered and modified, you only excrete 1 mil per minute. So that means 124 over 99% is reabsorbed. So you filter at this spot 125 mils per minute. You're only forming 1 mil a minute urine on average. That's kind of the average urine production. So the physiology is to teach students how to maintain that 125 mils per minute. It's directly proportional to the FP or NFP that we just calculated. However, the point of this slide is to emphasize to you how does the kidney regulate that GFR at 125 mils per minute. R, glomerular filtration rate, must be regulated at 125 mils per minute. Now, that will give you your normal urine production of about 1 mil a minute. So, this 125 mils a minute is highly regulated. It's proportional to blood pressure. So think about blood pressure. Blood pressure could fluctuate, but even if it did, GFR is highly regulated. Here's kind of the data that I usually see in books. Let's plot GFR against good old BP through a range of like 80 to 200. What's been observed is you can vary blood pressure and you won't really see a change in GFR. The nephron is highly regulated to kind of maintain a constant flow rate. You would expect that if blood pressure gets really high, that GFR would get really high, but it really doesn't. What you see is this kind of effect, a very gentle increase, and then something like that. Within a wide range of BP, the kidney keeps this constant. Okay? That's really what I want you to see from this. This is in your book. It's not in your book, but we are going to learn how GFR is regulated. The reason why you want to keep it steady, if GFR is too high, if you're filtering too fast, stuff's going through here too fast, basically, you don't have enough time to reabsorb it, and you'll lose a lot of the nutrients that your body needs. You won't conserve it, you'll lose it to the urine. If GFR is too low, you may reabsorb too much, including all the waste the body does not need. So it's very important to kind of keep it regular. And there's two ways we'll talk about how it's regulated. Of course, there's an intrinsic way, does not depend on nervous innervation. And there's also an extrinsic way. Let's do this way first. The autoregulatory way has a fancy name, flow-dependent tubuloglomerular feedback. Second way is basically the Rendon mechanism. Okay, so let's talk about that first. I want to look at this picture. Okay, so GFR regulation. Tubuloglomerular feedback. Now, for this to work, I'm going to throw in flow dependent. It depends upon the filtrate flow through the nephron, as pictured here. We're going to see that the nephron, the way the tube is set up, it can flow past itself to self-regulate. So let's just kind of follow the steps there. So this autocorrect thing can go either way. The disturbance could be the GFR is too high or too low. So in this example, it's too high. Right there. And whenever you autocorrect in physiology, if it's too high, you want to lower it. So just think that way. So, but let's go with this imbalance. It's too high. So that means, number two, the flow through the tube is too much. You increase the flow in nephron. It's a little bit too fast. So one thing I didn't teach, right? I did teach the DCT. There's a specialized part in the DCT called the macula densa. Increased flow here, you're increasing flow in the tube too much. You get to number three. You're going to increase flow past macula densa. Macula densa, that's in the DCT. And look where it is. It's right by the afferent arteriole. Now the thing it doesn't tell you that I wish it did, if flow is too fast, you don't have time to reabsorb sodium. Okay. Flow is too fast. Not enough time to reabsorb sodium. So let's think about this. You did not have time to reabsorb it. So it's not in the blood, it's remaining in the filtrate. So when that filtrate flows past the macula densa, it can detect that. It will detect there's increased amounts of sodium in the filtrate at the macula densa. Those cells are sensitive to that, the salt levels. Detects increased sodium in filtrate. Sorry, you're with me there. Flow is too fast, not enough time to reabsorb sodium. There's more of it in the filtrate. So that's really the key right there. Because the macula densa, this detector, can do things, self-regulate. So, number four, this is Paracrine response from macula densa to the afferent arteriole. paracrine. A paracrine is like it's a molecule from the macula densa to the afferent arteriole. Whatever the molecule is, it causes the afferent arteriole to constrict. I'll put VC. In this class, we've always known that to mean vasoconstriction. And when that happens, well, you're increasing the resistance to blood flow. I'll just put increase capital R, right? And if you do that, you're going to decrease pressure, decrease GFR, decrease HP, decrease GFR. So in this way, this all happened within one nephron. It's self-regulated. It was flow dependent. There was other words we like to use. Why do we say it's auto-regulatory? Well, there's nothing else happening here. It's all within the nephron. It's self-regulated. It depended on flow. And the tube was feeding back to the glomerulus because you went through the whole tube and you got right back to where you were. You sped back on yourself. Now, the opposite could be true. This only showed you one imbalance. What's the other? What if the imbalance was GFR was getting too low? Just reverse everything in your head. So, okay, now flow is too slow. We want to get it back up to speed. So you're going to decrease flow in the nephron. Okay, now flow is too slow. So now instead of not enough time, well, I guess you have too much time. So maybe you reabsorb too much sodium. So now when you get flow past the macula densa, well, you're going to decrease the flow past macula densa, for one. And secondly, it will detect a drop in sodium. Now the paracrine response will be, well, instead of a molecule that constricts, one that dilates, and instead of increasing resistance, now you drop resistance to blood flow. Hydrostatic pressure should increase to increase GFR. You just kind of flip the script. So, you know the reflex for the flow-dependent feedback, know it both ways. So this macula densa, it's an osmoreceptor, and there's something else in this area that also helps regulate GFR. And so this is kind of where I want to introduce this term, the juxtaglomerular apparatus. This picture we looked at for the break, we call this the tubular pole, but I want you to know number one and number two. Those cell types, number one, number two. Number one is macula densa. So, put this under juxtaglomerular apparatus. I'm going to teach two cell types. Books usually might mention 3 or maybe 4 cell types, but these two I want you to know. Number one, macula densa. It's the part of the DCT that's right by the vascular pole. Okay. So the physiology here is it's an osmoreceptor. It's a salt detector. Osmoreceptor. Like osmosis, you know, the diffusion of water depends on salt concentrations, right? So the osmoreceptor detects salt. Detects sodium levels, basically. The other one, the number 2, those are pointing to specialized smooth muscle cells in the TM. Remember arterioles have how many tunics? 2. TI, TM, no TA. So the TM is smooth muscle cells. So number 2 is pointing to cells called, let's see, juxtaglomerular cells. Let's call them that. Juxtaglomerular cells. You may also see the term granular cells. These, because the granules contain renin, these cells contain the renin. We refer to these cells as baroreceptors. They're sensitive to blood pressure changes because look where they are. They're in the arteriole, right? Baroreceptors. Detect changes in pressure. That's what a baroreceptor is. We studied the baroreceptor in the carotid sinus. These are kind of like them. They're detecting blood pressure changes at the afferent arteriole. So think of these JG cells, juxtaglomerular cells. They're specialized smooth muscle cells of the afferent arteriole. Specialized smooth muscle cells of the afferent arteriole. So that's what the number 2 is pointing to. And well, here's a flow chart from one of my histology books. Now it may be too hard to see. I'll kind of outline it for you. But this is kind of getting to our kind of second mechanism of GFR regulation, the renin. Okay. So here are the homeostatic imbalances of drop in blood pressure. Decrease blood pressure. Now we know now that the body's well regulated to help maintain blood pressure when it drops. Okay, so here you have osmoreceptors, and you have the JG cells, which are like mechanoreceptors, because they can mechanically sense a change in pressure because they're in the vessel wall. So I'll put JG cells, macula densa. Before I move on, I want to read what it says in here. Okay, so we have drop in BP. This says decreased GFR. Let me write that up here. We just talked about a decrease in GFR. Okay, if there's a drop in GFR, the flow is too slow, so you have more time to reabsorb sodium. So what would you detect in the filtrate? Less sodium. If you have slow flow, more time to reabsorb, you should detect less sodium. Okay, I'm praying this says less sodium. decreased sodium concentration in fluid. Yay. Okay, so it's good when the professor's right. Otherwise, we're all kind of screwed. Decreased sodium. All right, so that's kind of what we talked about prior. Now to move on. So these things will facilitate a renin release. Now, they both communicate together. But which cells actually have the renin? These ones. Okay, but they both kind of work together to release the renin. But I'll draw an arrow from here because these actually have the renin. Now from here, I won't write it on the board. We've talked about the RAS mechanism a lot this semester. You can review it. All the steps from angiotensinogen, right? Renin kind of cleaves it to angiotensin 1 and kind of goes to the lungs. And there's a converting enzyme that will convert Ang1 into Ang2. Remember that? Angiotensin 2 can constrict the blood vessels. We talked about that. And it can also, angiotensin 2, can facilitate aldosterone release from the adrenal cortex. That can go to, now we know, to DCT. You can facilitate sodium uptake. Water will follow. And both will increase blood pressure. Okay, so it's the same story that I've been kind of singing since the beginning. Okay. It's kind of like the bookends of this course, the whole renin thing. It's on the first test, it's on the last test. Yeah. Okay. Well, anyways, here's the whole corpuscle, and they're showing you the juxtaglomerular apparatus. You just have to know what to look for. Okay, here's afferent arteriole. They cut this open. Those must be the juxtaglomerular cells. Okay. There's the DCT or macula densa. Now, I like this figure. They show you the red glomerular capsule. What's this layer that was peeled off? Parietal or visceral?
Visceral. Yeah,
Yeah, it'd be the visceral layer of the Bowman's capsule. If you wanted to, like, if I said, what's the cell type? It's the podocyte, right? It's really the podocytes. There's the parietal layer of Bowman's capsule. So on this one, it's labeled, okay? So here, unlabeled, the name of the cell is podocyte. You can even see the filtration slits nicely. There's the glomerular capillaries. Here is, well, it's the juxtaglomerular cells macula densa of the DCT. On this one, it's labeled over there. This one, I would go for macula densa, not DCT. Specifically, right there is where you find the macula densa. Now, I like how they model afferent efferent arteriole. That's a regular looking arteriole, but you see how they have the spindle-shaped cells, and all the other cells are these kind of octagon-like cells. Those are supposed to be the specialized JG cells. Okay. This is a good place to stop. And we're going to do our kidney dissection. Now, I need a few minutes to pull things out. Let's reconvene in about 10 minutes. I'm going to go get students. You don't have to leave the room, but